0. So the nice thing about this range here is that you see j plus 1 is less than n, so this is 0. And j is less than n, clearly, so this is 0. So that means that we have these two groups here trapped between zeros, so this must be an isomorphism because the long exact sequence is exact. Now that's interesting, right? So that means that pi j of O of j plus 2 is pi j of O of j plus 3 is equal to dot, dot, dot. So you see the homotopy groups at high rank don't care about what the rank is. We say that the homotopy groups stabilize at high rank. And so we could define a group, we could define a homotopy group, which we might just call pi j of O. Okay? It's the stable homotopy group. And in fact, by these inductive limits that I was coy about talking about a while ago when we talked about classifying spaces, you can indeed make sense of an inductive limit of On to give an infinite dimensional group O. Well, of course, we can do the same thing with our other fibrations. We could take SUN plus 1 to act transitively on the 2n plus 1 sphere. And the stabilizer is SUN, as you recall. And so what we'll learn there is that pi sub j of SUN, see, we're going to apply exactly the same thing. And now j has got to be less than 2n plus 1. So 2n, actually. So this will be equal to pi j of SU infinity, if you like, which I'll just write as pi j of SU. So the homotopy groups of SU2 stabilize. And indeed, I could introduce this notation. Let me remind you, UF of n, which is O of n when f is R, U of n when f is C, and USP of 2n when f is the quaternions, H. And so remember that we had a C, which was 1, 2, or 4, the real dimension of those division algebras. And so we can summarize three cases all at once by saying that we have a fibration over S of C n plus 1 minus 1 UF of n here. And then because the homotopy groups are 0 for low dimensions in the sphere, we learn that pi j of UF of n goes to pi j of UF of n plus 1 is, first of all, an isomorphism for j between 0 and c times n plus 1 minus 3. And you can squeeze a little bit more out of the exact sequence. It's an epimorphism. It's onto for j equals c n plus 1 minus 2. So just as some examples, let's look at the SU2 case. So pi 1 of SU2, well, if you apply this rule over here, SU2 is already in the stable range for j equals 1, so that's equal to pi 1 of SU3, which is equal to pi 1 of SU4, and so on. And similarly for pi 2, j equals 2 is still in the stable range for SU2. You see, for SU2, if I took n equals 2 and c equals 2, then I would get into the stable range for j less than or equal to 2n minus 1. Okay, so for n equals 2, pi, I can go up to pi 3. So we know these are all the same. Pi 3 of SU2, pi 3 of SU3, stabilized. But pi 4, not. Pi 4, you have to go higher, because it turns out that pi 4 of SU2 is Z2, but pi 4 of SU3, as we'll see, is 0. That's not supposed to be obvious that pi 4 of SU2 is Z2. It's a true fact. Okay. So the homotopic groups of the classical Lie group stabilize at high rank. So let's look at some values for low values of J. Let's start with pi 0. So pi 0 of SON is pi 0 of UN is pi 0 of USP to N is 0. Okay? And the way you prove that is you have these classical theorems, the spectral theorem, where you can always conjugate your matrix into a maximal torus. And you see a torus is connected, and so you can take a path in the torus to the identity, and then when you're conjugating, you conjugate the identity, you get 1. So so that's the proof that these are all connected, and of course you all will note that ON is a little different. Pi 0 of ON is Z2. How about pi 1? Well, every Lie group has every compact Lie group has a simply connected universal cover, simply connected and connected universal cover. And so then G will always be able to form G tilde like gamma, where gamma is a subgroup of the center. And then pi 1 will be equal to gamma. We've seen that many times. Now I give you in the notes a list of the simple Lie algebras. They're compact, simply connected, connected covers, and the centers. Okay, and so that tells you what to see. Now, without invoking theorems like that, we can prove some things for ourselves. We've seen that SU2 is already in the stable range, but you see we also know that SU2 is the 3-sphere, so pi 1 of the 3-sphere is equal to 0, so that's a proof that pi 1 of SUN is 0. So SUN is simply connected. On the other hand, SO3 is in the stable range for SO3 is in the stable range for the orthogonal group. So pi 1 of SO3, well, that's S3 mod Z2 by a free quotient. So that's equal to Z2. So that's equal to pi 1 of SON for all n greater than or equal to 3. Okay, so that gives us pi 1 of the SO groups. How about USP? Well, you see USP2 is, again, SU2, which is the 3-sphere. And so USP2, rank 2 is already, rank 1, USP2 is already in the stable range for the USPs. So pi 1 of USP2n is equal to 0 for n greater than or equal to 1. Okay, so those are pi 1s. What about pi 2? Well, there's a theorem of Cartan that says that every compact Lie group has pi 2 equals 0. So pi 2 always vanishes for a compact Lie group. And it's very reasonable. It's true for U1. Compact Lie groups are made by gluing together odd-dimensional spheres, so it's quite a reasonable statement. We can prove it because, again, for SU2, for SUN, SU2 is already in the stable range for pi 2, as I said. So this is equal to 0 because this is the 3 sphere. The same story holds for USP2. Okay, so those are in the stable range. And what do we do for SON? Well, pi 2 of SO4 is in the stable range, but you see SO4 is SU2 times SU2 divided by the diagonals E2. But for a discrete cover, higher homotopy groups are the same as the covering space. As we saw, we proved that already. This is a product of 3 spheres, so this is 0. So that checks that pi 2 of the orthogonal groups are orthogonal and special or orthogonal are 0. And finally, let's do pi 3. Okay, so for SUN, we're already in the stable range for SU2. SU2 is the 3 sphere, so that's Z. Same story for USP. And what about the SOs? Well, there's a special isomorphism of SO5 is USP4 mod Z2. So I always explain that in my group theory course. That comes about from relationships of Clifford algebras. Now we just said that pi 3 of USP4 is Z, so we know that pi 3 of SO5 is Z, and that's in the stable range, so we're done. Okay? So just using these elementary considerations, we've determined the first 4 stable homotopy groups. Are there any questions about that?
So those UF are the UN at S. So for example.
Yeah, but remember that that's absolutely true. And the one place, okay, so here, so what's the relation between the specials and the non-specials? So, okay, so Ln is going to be SON times Z2. Now, as a group, it might be a semi-direct product, but as a topological space, it's just crossed with Z2. UN is equal to SUN times U1 divided by Zn. Okay, so now these cross product with Z2 and division by Zn, those only matter when we're looking at pi 0 and pi 1. And then for the higher homotopy groups, there's no distinction between these two guys. There's no distinction between these two guys for j greater than 1, j greater than 0. And for these, pi j of un is equal to pi j of sun for n greater than or equal to 2, and pi j pi 1 of un, as we just saw, is z. I guess I didn't say that here, but I should. Yeah. Okay. Now, the beautiful result of Bott. Called Bott periodicity says the following. It says, first of all, that pi j of u, these stable homotopy groups, is isomorphic to pi j plus 2 of u for all j greater than or equal to 0. And pi j of O is isomorphic to pi j plus 4 of USP for all j. And pi j of USP is isomorphic to pi j plus 4 of O for 0 less than or equal to j. Yeah?
Where here O means an arbitrary O and not the infinite dimensional one.
No, it means it's the same. That's the point.
Oh.
The point is,
Oh, right.
if you like, if you're scared of these infinite groups, then just read this as in the stable range. ON with n in the stable range. Okay? If you want to stay with finite dimensional manifolds, you can. Okay? You don't have to believe me that there's an O infinity. But there is an O infinity, and so this is true for those, but it's also true for anything in the stable range. Now notice that if you put together these two statements here, immediate corollary, here's the periodicity, is that pi j of O is pi of j plus 8 of O. Okay. So, now we can just, now if you're granted this, and in the rest of this lecture I'll be saying something about, a little bit, about why this is true. We don't have all the machinery we need to prove it, but I'll try and make it plausible to you. But granted bot periodicity, which is a very deep result, we can at least plot or list the stable homotopy groups of the classical groups. So we have j is 0, 1, 2, 3, 4, 5, 6, 7, 8. Okay? In fact, I don't even need to list 8. Because 8 is congruent to 0 mod 8. Okay. So, what do we have for pi 0? Well, pi 0 of O is Z2. How about pi 1? Pi 1 of O is Z2. How about pi 2? Pi 2 is always 0. How about pi 3? Well, we saw that pi 3 is Z. How about pi 4? Well, we didn't calculate pi 4 of O. We didn't calculate pi 4 of O, but we have pi 4 of O is pi 0 of USP, so that's 0. Okay, so let's look at USP. Let's fill in the table this way. USP, pi 0 is 0. What's pi 1? 0. Pi 3, Z. How about pi 5? Let's finish now with pi 5 of O. Pi 5 of O is going to be the same as pi 1 of USP, so that's a 0. So there's a 0 here, and there's a Z here. Now we can do the same story over here, right? So pi 4 of USP is pi 0 of O, so there's a Z2 there. Similarly, a Z2 here in pi 5, a 0 here, and a Z. And then the unitary groups are very easy. This is connected. We have Z, we have Z, we have 0, we have Z, we have 0, we have Z, period 2. Yeah.
So you mentioned that for higher homotopy doesn't depend on its OM or SOM. For example, if you take pi 0 of O and pi 8 of O, because it's periodicity, you say pi 8 of O is Z2 or 0?
That's right. So pi 8 of O, which is pi 8 of SO, is Z2. Look, they don't differ by that much. Topologically, O is just 2 copies of SO.
But I would say pi 8 of SO is pi 0 of SO. So
No, I didn't say that.
okay.
I didn't state the periodicity for SO. I stated the periodicity for O. Any other question? You were right. It would be wrong if I had put SO there. Okay. Now, it's easy to remember the periodicity for the unitary groups, right? I mean, all you have to remember is that U1 has pi 1 as Z and is connected. That's all you need to remember. You can do that. It's a little harder to remember the stable homotopy groups for the orthogonal groups. Okay, but if there's a great mnemonic for doing this, okay? If you're ever stuck on a desert island and you need to know the stable homotopic groups of the orthogonal groups, this is what you do. You sing Z2, Z2, 0, Z, 0, 0, 0, Z, okay? And you'll never forget the stable homotopic groups of the orthogonal groups. All right. I call that the bot song. All right, so now we're going to apply this to Stiefel manifolds and Grass-Bunnians. So remember, let me remind you that Vk of Fn is equal to the space of all k-dimensional subspaces of Fn equipped with an orthonormal basis. All right? So let's consider the fibration. Un minus k goes to UF of n over Vk of Fn. You see, the unitary group acts on these k-dimensional subspaces and also takes one orthonormal basis to another. And if we want to calculate the stabilizer group, we could take the k-dimensional space with its standard orthonormal basis, and the unitary matrices which will stabilize that look like a 1 here and anything on the orthogonal complement. Okay? So that means that this is a homogeneous space, and therefore we have this fibration. Okay, so now let's look at our long exact sequence. Okay, so our long exact sequence, erase this, is a piece of it looks like this. So we'll start in the fiber here. Okay, so we map the fiber into the total space. And then we project to the base. And then we have a connecting homomorphism to the fiber. And then we embed in the total space. And so on. All right. But now we've learned this nice stability of the homotopic group. So if J is less than or equal to C times n minus k plus 1 minus 3, okay, then this is an isomorphism, and this is an isomorphism, and this is an exact sequence. This is trapped between two isomorphisms. So this being an isomorphism means the kernel of this map is 0, means the image of this map is 0, but the image of this map, but the kernel of this map, namely 0, is the image of this map. But this, you see, is onto. Okay, so the kernel of this map is everything. So the image is 0. So this is just 0. Okay, so that implies that pi j of Vk of Fn is 0 for 0 less than or equal to j less than or equal to c n minus k plus 1 minus 3. Actually, we can do a little better because, as I said before, you see, if j is c times n minus k plus 1 minus 2, then this map is still onto. So, and this is an isomorphism because I have a j minus 1 here. And so it's still true. So I can, in fact, put 2 there. Okay. Well, that means that the low homotopy groups of the Stiefel manifolds, low in the sense of low J with respect to n minus k, they are 0. And so that suggests that if I take a limit again, as n goes to infinity of vk of fn, that's going to be, so let's call that vk of Hilbert space. So that's going to be k-dimensional subspaces of a Hilbert space equipped with an orthonormal basis. That should be what we call EUF of k. Because we have a free, saying something a little wrong here. Yeah, I'm getting ahead of myself. That's what I'm saying that's wrong. Okay. So this space is contractible. That's what we've learned. All its homotopy groups. Now, remember that we still can quotient by the unitary group, UK, acting on the Stiefel manifold to give us the Grassmannian, right? So we also have a fibration, UF of k, into VK of Fn. This has a free right action going down to the Grassmannian of k-planes in n space. So I'm forgetting, when I do that quotient, I'm forgetting the particular orthonormal basis. I have the Grassmannian of k-planes in Fn. It's just the space of all k-dimensional subspaces of Fn. Now, okay, so UF of k has a free action on this. I can take this limit here. So VK of H also has a free right UF of k action. And therefore, VK of H is what we call EUF of k, and the Grassmannian of k-planes in Hilbert space is BUF of k, the classifying space. So remember, I told you that there's this Platonic bundle for a given group, in this case U of k, from which I can pull back all principal UK bundles. And so this is the classifying space. And in subsequent lectures, I'm going to be aiming to explain more deeply why that's the case and really show you how to pull back, how to construct vector bundles over this space and why they all pull back. So we're going to come back to this. But for the moment, we're going to do something different. For the moment, we are going to take this vibration and apply the long exact sequence yet again, this time inputting the fact that the Stiefel manifolds have vanishing homotopy groups for low j. So now we're going to take pi j of vk of fn. Total space goes to the base space, to the Grassmannian. Then we have a connecting homomorphism to UF of k. And then we insert that into VK and Fn. Okay? But now, if 0 is less than or equal to j is less than or equal to c times n minus k plus 2, n minus k plus 1 minus 2, then, as we've just shown, this is 0, and this is 0, and therefore, this is an isomorphism. All right? So let's bring out the symmetry of this. Let's define GR sub nm of f to be GR of n planes in Fn plus m. Remember, there's a symmetry in the Grassmannian between the planes and their orthogonal complement. And so what the stabilization tells me, if I now also stabilize on this k here, okay, I find that pi j of the Grassmannian nm of f is independent of n and m as long as 0 is less than or equal to j less than or equal to c, n plus 1 minus 2, and j is less than or equal to c, m plus 1 minus 2. So once again, we can take a limit when n and m go to infinity to get a different kind of classifying space.
Yeah, like you guys said.
So that's denoted so what is this? This is the limit as n and m goes to infinity of uf of n plus m divided by uf of n times uf of m. So this space, by definition, is called BUF. So it's different from BUF of k. There's a specific k there. Here I'm stabilizing in two different ways. And this is usually written as BO, when f is r, BU, f is c, and BSP, when f is h.
I'm sorry.
Yeah.
So you said this space is contractible. So
Oh, I didn't say Grassmannian is contractible. I said that the Stiefel manifold, I said that the k-planes in Hilbert space with an orthonormal basis is contractible.
oh, it's just isomorphic to pi j.
Then when I divide the Stiefel manifold by the unitary group, I get the Grassmannian, which is most definitely not contractible. It has lots of interesting topology. And what we've shown here is that for low values of j, in this sense, pi j of the Grassmannian is pi j minus 1 of the unitary group. Okay? You all with me? And then, since the unitary group stabilizes, since pi j of the unitary group stabilizes for large k, I can make this whole thing independent of k, if you like. And then I just wanted to write this a little more symmetrically, like that. So now let's return to this boxed equation here and try and write it in a more suggestive form. Okay? So let me remind you that, recall that pi j of a space for the base point is isomorphic to pi j minus 1 of the base loops of that space, where, of course, the base point is the constant loop at x naught. We've seen that before. Remember that this omega sort of adds an extra circle, if you like. Okay. Remember how we proved that? We proved that using the path vibration. All right, so I shouldn't be erasing this definition, but I just did. But using that definition, and this statement here, and this statement here, we see that pi j of the loop space of BU of BUF is equal to pi j of UF for all j greater than or equal to 0. So I shouldn't have erased that. So BUF is the limit as n and m goes to infinity of the Grassmannian of n and m in f. Okay. So what did I do here? I put together definition, this result, and stabilization. Now, you might be tempted to conclude that the loop space on BU, or if you prefer, the loop space on the Grassmannian for large N and M, is homotopy equivalent to the unitary group. Right? You might be tempted to conclude that because the homotopy groups are isomorphic. Yes? Yeah. But now you have to be careful. So there's a Bourbaki sign here. Pi j of x isomorphic to pi j of y for all j does not necessarily imply that x is homotopically equivalent to y. And a simple counterexample is to consider RP2 times S3 as x and S2 times RP3 as y. Okay? Now, do you see why they have the same homotopy groups? Hint, think about the covering space, universal cover. Remember that for a discrete group, the above pi 1, all the homotopy groups are equal on the covering space. You see, they have the same universal cover, S2 times S3. And they also have the same pi 1 because both of them are quotients by Z2. They're both quotients by Z2, but in different ways. The Z2 acts on the 2 sphere here and on the 3 sphere here. But nevertheless, they have isomorphic homotopy groups. Now, I claim that they're not homotopic equivalent. Now, how do we know that? Well, we didn't discuss it in too much detail, but I talked about a characteristic class. And I've also told you that characteristic classes are invariant under homotopy equivalence. Okay. So the only characteristic class you know about, officially, is the first Stiefel-Whitney class, which measures orientability. You see, this is orientable. This is not. So they can't be homotopically equivalent. Okay.
Excuse me.
Yeah.
Could you add some other constraints so that it would imply that x and y are homotopically equivalent?
Yes. And that is the profound Whitehead Theorem, which I mentioned a long time ago. So the Whitehead Theorem says that if there's a map f from x to y, which induces an isomorphism on the homotopy groups for all j, then f is a homotopy equivalence. Okay? So, in this case, it is true that that the base loops on BUF is homotopy equivalent to the infinite unitary group. It is true. And I am not going to prove that the following map induces the isomorphisms, but I am going to give you the map. So to give the map, let's do the following. Let's take f to n, and let's split that up as fn direct sum 0, direct sum, let's split that up as fn direct sum fn. In other words, we take the two n coordinates here, and the first n coordinates go in here, and the second n coordinates go in here. Okay. And now we're going to look at the what I call the path space on the Grassmannian of n planes in F2n, which is going to be the space of all paths from Fn plus 0 to 0 plus Fn. Okay? So these are 2 points in the Grassmannian. So here's my Grassmannian. I fix 2 points. Let's call this P1 and P2. So I have P1 and P2 here, and now I'm looking at all paths from P1 to P2. Okay, so it's an infinite dimensional space. And as we've discussed, this path space is homotopically equivalent to the based loops on the Grassmannian. Right, because all I have to do is choose some reference path, any one you like, that goes from here back to here. And then if I compose these paths with that reference path, then I get a closed path. Right? Okay, so it's technically easier to work with this open path space, and that's why we're using it.
But it always has to pass the other.
Pardon?
All this loop will have to pass the P2. It's not ordered.
Yeah, but that doesn't matter. You can move P2 around. Okay, so what's the map? So I'm going to give you a map from UF of n into the path space of GR and of n planes in 2n dimensional space, which induces this. And so the idea is I'm going to give you, for a G here, I'm going to map it to what's called a piece of G, a path in here. And the path is the following. Piece of G of T is equal to the span of the following set of vectors, V times cosine pi t over 2, GV of sine pi t over 2, where V lives in Fn plus 0. I guess strictly speaking, just Fn. Okay, so you see at t equals 0, this part is 0. So I have V comma 0, so the initial point is right. At t equals 1, the cosine is 0, the sine is 1, and G is unitary. So I get this space here. So for each t, I get a point in the Grassmannian, and how this path evolves depends on the unitary matrix G here. Okay, now it's not supposed to be obvious that this induces these isomorphisms on homotopy groups, but it is. And we're going to discuss the sort of the inverse map in a little more detail. And the way you prove that this is inducing those isomorphisms, however, is by Morse theory, which we're coming to. All right, so this induces a isomorphism of the homotopy groups for J, which is sufficiently smaller than n. I won't be specific about just how smaller, but if you take now the n goes to infinity limit, then you get exactly the statement that I made here, that the loops on the Grassmannian give me a space which is homotopically equivalent to the unitary group. Now, we saw here that if we took the Grassmannian of k-planes, then we got a classifying space for principally UK bundles. You might ask yourself, if I take both n and m to infinity, is this some kind of classifying space? So is BUF a classifying space for something. Is it a classifying space for something? And the answer is almost, yes. In fact, if I take Z times BUF, then that is a classifying space for a cohomology theory called K-theory. And so we can, in fact, define K0, let's say KUF of 0, of a space X is the space of homotopy classes of X into not quite BUF, but Z times BUF. Oh yeah, so one other thing I forgot to mention. I motivated using the exact sequence here that this space is contractible. And as an exercise, you might try and prove that using the Hilbert-Hotel argument that we had before. Remember, we had the Hilbert-Hotel argument to prove that the infinite dimensional sphere in Hilbert space is contractible. Remember that? So a variant of that argument proves also that the Stiefel manifold in Hilbert space is contractible.
Question.
Yeah.
Could you comment about how one of the each copy of BUF inside of that inside of the K naught of UF, what it looks like inside the K theory? The BUF isn't quite class.
Yeah. Yeah. So this Z, I was actually going to come to something closely related to that. This Z is classified as something called the index. So in the simplest case, if I take X to be a point, then if I have a K-theory class over a point, that's just a difference of two vector bundles. And what the Z is n minus m. So that's the answer to that question. All right. Now we've got this map here. We've got this map here. And now I'm going to try and construct a kind of inverse to it. And that, once we get that inverse, we will start to understand where Bott periodicity is coming from. Okay. Now we have to, and this is essential for what I'm about to say, we have to put F equals C, complex numbers. Now I'll say what happens when we put F equals R or H in a moment, later. But what I want to do is I want to do something like take a map from the Grassmannian into something like the loops on UN. Now here I really mean UN with the complex numbers. Okay? See, what have we done here? Here we've, roughly speaking, given a map from the unitaries into loops on the Grassmannian. Now I'm going the other way around. I want to do maps from the Grassmannian into loops on UN. Now right away we have a little complication, right? Because pi naught of UN is, pi naught of loops on UN is pi 1 of UN is Z. And indeed, what are these components? This is a very intuitive thing. If I have a path of unitaries, G of T is a path of unitaries, closed path of unitaries, then I can take the determinant of that G of T. And so T goes to G of T is a map of the circle. If I identify T with T plus 1 into the circle, into U1. So that has a winding number, you see. Okay? And that winding number measures the path component. So the winding number of the determinant of G of T measures the component. So that means that this space has many components. Now here I was talking about a connected space, the Grassmannian of n planes in F2n. But you see, what we could do is we could look at the Grassmannian of all planes in F2n, which of course is a disjoint union from k equals 0 to 2n of the Grassmannian of k planes in F2n. Okay? So this space has 2n plus 1 components. Now, it would be wise to write this a little bit differently. Let's write this as the Grassmannian of n plus k and n minus k planes. Okay? And so my k now is lying between minus n and n. Just rearranging what I mean by k. So what we're going to do is I'm going to now define a map, Grassmannian, of the total Grassmannian of F2n into loops on U2n. And how am I going to define it? Well, once again, this is homotopically equivalent to loops to paths, open paths from +1 to -1. Okay? So inside the unitary group, here's the unitary group, U2n, and we have the identity, and we have the matrix -1, and now we're going to look at all paths. And again, we could choose a reference path that goes back and use that to identify with closed loops. Okay, so what's the map? So if I have a vector space V in F2n, then I map it to the path GV of t, which is e to the I pi t times the orthogonal projection operator onto V, direct sum, e to the minus I pi t times the orthogonal projection operator onto times the orthogonal projection operator. Okay. So you see that that defines an open path, and clearly at t equals 0, this is the identity, unitary transformation, because the I pi t's are 1. And I have the sum of projection operator and its orthogonal complement, so that's the identity. And at t equals 1, all I do is have a -1 here. But, you see, this projection operator depends on V. So this is an interesting map from Grassmannian into the space of loops on the unitary group. Let's for fun calculate its, let's calculate its winding number. Let me let you do that to make sure you're still following. So can anybody do that? What would the winding number be? So let's for simplicity suppose that V is equal to let's say C I. I just stressed before that I'm talking about the complex number, so let me be honest about that. Okay, so let's let V be C to the n plus k, okay, plus 0. Can you calculate that winding number for me? So what does this G sub V look like, right? So it's going to be e to the I pi t, e to the I pi t, e to the I pi t. That's the projection operator onto the first n plus k. And then for the next n plus k, I have e to the minus I pi t, e to the minus I pi t, e to the minus I pi t. Okay? So now we take the determinant of this matrix. So this is G sub V of t. And the determinant of G sub V of t. Anybody?
That's e to the I pi t times n plus k plus n
Very good.
minus n
E
minus
to the
k
I pi t times n plus k
minus
times e to the minus I pi t times n minus k. Can we simplify that?
Yeah.
So that's equal to e to the 2 pi I kt. Okay, so let's just to be concrete, let's choose the path that goes back to be the inverse path. Let's call it g sub c to the n plus 0. Okay, k equals 0 for that standard space. Okay, so then the determinant is 0. Okay, so now what's the winding number? It's k, right? Okay, so so you see that these guys correspond to winding number k, and so they line up. So these components, labeled by k, which is going between minus n and n, sit in the z this way. We have 0, 1, got up to n, n plus 1, and so on. We have 1 here, we have minus 1, down to minus n plus 1. And so we're mapping to these here. And k equals 0 is sitting in there. And we can call this k here is the index of this path g of v. So in general, it should be easy to see that this is the dimension of v minus the codimension of v. So it does look like an index, doesn't it? Okay. All right. So now, having dispensed with that little complication, let's now look at the map of Grassmannian of n-planes into C2n, mapping into the loops, the base loops, on SUN. Okay, that's going into the 0th component. For the 0th component, you see the loops on UN is the same thing as the loops on SUN. Okay. Now, Bott's idea, Bott's beautiful idea, translated into modern terminology, modern physics terminology, was to study the point particle moving on the group manifold. In the left-right invariant metric. Okay? So what we do, so what's the left-right invariant metric on SUN? So it's D or UN or any compact group. It's a trace of G inverse dg tensor G inverse dg. Now for a simple Lie group, the left and right invariant metric is unique up to an overall constant. That's why I'm not telling you the trace and what representation. Well, let's take the trace and the fundamental representation, but you can take it in any representation. Any two will differ by a constant. All right, so then we look at the nonlinear sigma model action for a path. So yeah, I'm calling it S. So S of P. Well, in general, that's d by dt. That's dt of g mu nu of P of t, P mu dot, P nu dot. And to be really concrete, that's d by dt. That's dt of the trace of g inverse dg by dt squared. So that's our action principle. Okay, now it's an easy matter to get the equations of motion from this action. I won't go through it. The equations of motion are d by dt of g inverse dg dt is equal to 0. So solutions of the equations of motion put this G inverse d by dt equals A, where A is in the Lie algebra. The Lie algebra is the Lie algebra of 2n by 2n anti-Hermitian matrices. And therefore, G is equal to G naught times e to the AT. Okay, now what are we going to do with this theory? Well, the idea here is to study Morse theory. So I'm going to say more about Morse theory after I explain the basic idea of the periodicity theorem, and then we'll go back and say more about it. So, in a nutshell, Morse theory says if I have a real valued function on a manifold, and I know its critical behavior, then I know something about its topology. And in particular, if I look at the stationary points, at the critical manifolds of that manifold, I can sort of build up the whole manifold on which the function is living. And I'll say some more about that. For the moment, we're just interested in solutions of the equations of motion. So paths, let's call them on-shell paths through G equals 1. Remember, we're interested in paths from 1 to minus 1. Therefore, look like T goes to exponential of pi t a, where A can always be diagonalized to look like IA1 through IAN H, where the sum of the AI's is 0, because of an SUA. Now I want this, I want G of t at t equals 1 is minus 1. That's for the other end of my path. So that implies that all the a sub i's are odd integers. Okay. So the action, then, for such a path, an on-shell action is pi times the sum of the ai squared. So what's the minimal action path? You tell me. How do I minimize the action? Plus or minus 1, right?
Yeah.
So the minimal action path has the AIs equals plus or minus 1, but there's something else. All right. So we have to have n AIs are plus 1 and n AIs are minus 1. All right. So, okay. So that means we're looking at the orbit under SU2n of this matrix I times minus I, where we look at H inverse H, but that set is equal to the Grassmannian of n planes in C2n. You see, this is equal to U2n divided by UN times UN, this homogeneous space, right? Because the stabilizer of this, by definition, it's transitive action of U2n, and the stabilizer is UN times UN. But this is the Grassmannian of n planes in 2n-dimensional space. So we found something, Bott found something very interesting. So the space of minimal action paths is equal to this Grassmannian of n planes in 2n space. Okay. So now you apply Morse theory. Okay. So what Morse theory is going to tell us is the following. We have a Morse function on our manifold. We look at its critical manifolds, and we look at the lowest one, okay, and that gives us some manifold. And then we look at the next one, okay? And the next one is going to have what's called a Morse index. And if the Morse index is some capital N, then up to homotopy groups capital N, the manifold is the same topologically as the minimal critical manifold. I'm going to explain that in more detail in a second. But, so what Morse theory does is you calculate the Morse index of the non-minimal action stationary paths is, it turns out, I'm not going to show this, greater than or equal to 2n plus 1. So, you see, there are many solutions of the equations of motion that take us from 1 to minus 1. You think of the group as some kind of, compact space with, think of it in terms of its maximal torus. You could have wrapping many, many times around the maximal torus before you end up at minus 1. So there are many, many solutions of the equations of motion. These solutions, the solutions parameterized by the Grassmannian, are the minimal action solutions. But then there are other solutions which have higher action. They're stationary, but they have higher action. So that means, right, that means that they can't be absolute minima of the action. There must be some directions in field space that minimize, that take you off. So there must be some unstable modes, okay, some negative modes that will take you down in action, even though it's a stationary point. It's not an absolute minimum. And then what happens is that most of the modes, infinitely many modes, go up to infinity, but there's a finite number of modes that go down. So to get some intuition for this, think about, instead, let's think about closed loops on the n-dimensional sphere, okay? Think about closed loops on the n-dimensional sphere that begin and end at the south pole. So the minimal length curve is the constant curve, right? So it just sits here. But of course, what are the other geodesics? The other geodesics are great circles, okay? And we could go many, many times around those great circles. So the first non-minimal on-shell motion is one that goes around the great circle. Now you see there are many of those. Now most of the perturbations of this path will just increase the action, or the geodesic length. We could use one or the other. Most of these motions, infinitely many of these variations of the path, will increase the action. But there are a finite number of motions, namely, I slip this off the back of the sphere, okay, which lower the action. Okay? And how many of those are there? Well, you think about it, there's an Sn-2 dimensional space of perturbations in which you could lower the action. And so in this case, the Morse index would be n-2. And what you learn, this was what Morse found before Bott, this is why it's called Morse theory. What Morse found was that if you take loops on Sn, it has the topology where you're gluing a sphere, roughly speaking, of dimension n-2 to a point. And then the higher solutions of the equations of motion are gluing higher dimensional spheres. Okay. So, so if we apply that now to our case, so I'm just telling you that the higher solutions of the equation of motion, higher action solutions of the equation of motion, have a Morse index, which is growing like n, and therefore, what we can conclude is that pi j of the Grassmannian of n planes of C2n is isomorphic to pi j of now the loops in SU2n, remember we're still in the zeroth component, which by general nonsense is pi j plus 1 of SU2n. And now this is valid by Morse theory for j up to 2n, because of what I was just saying. So this is, Morse theory gave us this. On the other hand, the long exact sequence arguments that we had before showed us that pi j of the Grassmannian of n planes in C2n is isomorphic to pi j minus 1 of SU2n for 1 less or equal to j less or equal to 2n plus 1. Okay. Well, there you go. There you go. That is that for low values of j. So that's how Bott proved Bott periodicity in outline. And if we put back in the unitary group, we get pi j minus 1 of un is pi j plus 1 of un. And that's for all j less than 1, less than 2n. And taking the n goes to infinity limit, we have what I said before, pi j is pi j plus 2 of u. Now we can also state that, since we have a map and isomorphisms of homotopy groups, we could also state that analogously to what we had before. So remember, this line of reasoning gave us that omega, the loops on BU, is homotopically equivalent to U. Similarly, this line of reasoning gives us that the loops on U is homotopically equivalent to Z times BU. Now that Z, as I just discussed, are these different components of U. Okay? Now, I also said that this is a classifying space for something. This can also be thought of as the space of all Fredholm operators on Hilbert space, and then that Z is again the index of the Fredholm operator. Yeah.
The Morse index that we described there, should I think of that as being similar to the Morse index used when discussing Morse theory for, say, surfaces, and you want to look at topologically equivalent surfaces?
Yes, it is. Except there's some subtleties that I'm scanning over, because we actually have a degenerate Morse function. We don't have an isolated critical point, right? We have this whole Grassmannian. So you talk about the non-degeneracy condition on the orthogonal directions. We're also in infinite dimensions. There are some subtleties, which I'm not going to discuss now, and I'm not going to discuss next time. Now we're out of time, and there's another talk. So next time, I'll just tell you, without going into so much detail, what the pattern of these loop spaces looks like for the real case. And I'll say a few words about Morse theory. And then if the lectures have been getting too hard, we're going to start a new chapter, which is a lot easier. We're going to start talking about some vector bundles.
Those Fredholm operators.